Hello. This lesson we're going to focus on another shortcut for taking derivatives. It's called the chain rule. And in class we discuss a lot about the reasoning behind this, but the purpose of this video is primarily to focus on just the method itself. All the other things, the details like using technology to support our work and understanding our results and those kinds of things, those are always going to be requirements. But sometimes on these videos I focus just on the Khan Academy kind of stuff. Alright, so the first thing, as a reminder of the technology requirements, you can use Desmos to graph the derivative just using this notation. This basically says if this is your function, then the derivative of the function with respect to x is right here, and that gives us the green graph. And the other thing we can do once we have this is recognize, for example, that the original function is always increasing, except for right here at negative 1.5, and therefore the derivative itself is always positive, except here where it's 0. The slope of the tangent is 0 at the same spot. So those are the things that we are to think about. So when I take my derivative, I should get a function that's definitely always going to be positive, and it's shifted over 1.5. So that's kind of my objective. So carry on then. I have to understand that the function I'm given is actually a composite function. And what do we mean by a composite function is there's sort of a chain of dependency. And in this case, I have a function 2x plus 3, and that gives me the g value. Once I have that g value, I can put that into the f of x function and get another value out of it. So in other words, the function I'm shown is really f of g of x, which is the g function 2x plus 3 inside the f function, fifth power. What we learned in class is the derivative of a composite function is the derivative of the outer function, dependent on g of x, times the derivative of the inner function, which is the derivative of g of x itself. So in process, it's good to show the first step, even though most people can and should do this stuff in their head. The first step, though, is to multiply the coefficient by the power, drop the power by 1, and now the chain rule says, and don't forget to take the derivative of the inner function as well. So notice I didn't take the derivative of 2x plus 3, I simply set it up. Notice I didn't finish subtracting 1 from 5, I just set it up, and I didn't multiply the coefficient by the power, I just set it up. So if you set up the derivative first, you're going to have a much better chance of success in this process. Plus you'll remember it better. Now, here, 5 times 2x plus 3 to the fourth. The derivative of 2x plus 3 is 2, using the power rule or using common sense, because it's a linear function. 2 times 5 is 10, and this is my derivative. Of course, we're going to check that. So here, again, I remind us that the derivative is 10 times 2x plus 3 to the fourth power. And this blue graph corresponds to what used to be the green graph earlier. And now I can see that the blue graph corresponds to the green graph. Therefore, the derivative the computer gave me is the same as the derivative that I got using the chain rule. If these are different, the graphs are different, that means you applied the chain rule incorrectly. Just as a reminder, Wolfram Alpha is available to you, and it might be hard to see here, but you ask Wolfram Alpha to take the derivative with respect to x of my composite function, and straight up it just says 10 times 2x plus 3 to the fourth. Here's some fancy notation, and they're sort of showing you the chain rule using better notation, in my opinion, than I've explained to you. I would encourage you to look on Wolfram Alpha and look for the steps, because it's kind of... Well, it's just like right here. You can see it's using a very similar form to what I did in my work. So, it's a great source of information. Again, for the remainder of these videos, then, I'm just going to concentrate on the method or the procedure and identification of composite functions. So I have an inner function composed inside an outer function. It's important to identify those. In this case, g of x is 4x minus 1, and the f of x is x to the 8th power. And so if I compose them, I get 4x minus 1 to the 8th power. Once again, the derivative of a composite is equal to the derivative of the outer function, dependent on the inner function, times the derivative of the inner function. So, in this case, 8 times 1 is 8. Drop the power by 1, and mark the derivative of the inner function. So, dropping the power by 1, I get 7. The derivative of 4x minus 1 is 4. 8 times 4 is 32. Here's my derivative. Don't forget to check it. Make sure that you didn't forget. The most common mistake here, of course, is students forget to take the derivative of the inner function. They end up with a function that is a quarter of its appropriate size. So, moving really slowly. composite, the inner function is 5 minus x this time, and the outer function is x to the negative fourth this time. So once again, the derivative of a composite is equal to the derivative of the outer function, dependent on the inner, times the derivative of the inner. That generates the following. Negative 4 is the exponent multiplied by the coefficient. Drop the coefficient by 1 and set up the derivative of the inner. This is negative 4, 5 minus x to the negative fifth. The derivative of this line is the slope of the line, which is negative 1. Negative 1 times negative 4 is 4. And for cosmetic purposes, I also wrote this without negative exponents, so we can see that this is really mostly a very decreasing kind of function going on here. So, another example. This time, though, we notice that the inner function is not linear, so it's going to require something a little bit more complicated than we've seen. And here, g of x equals x cubed plus 1, f of x equals x to the fifth. And so here we have x cubed plus 1 to the fifth. The derivative of the composite is equal to the derivative of the outer times the derivative of the inner. So 5 minus 1, derivative of the inner function. The derivative of x cubed plus 1 turns out to be 3x squared. So multiply 3x squared times 5, you get 15x squared, times the inner function to the fourth power, 1 power reduced from before. And finally, about as complex as we can get, we have a radical in the denominator with a cubed function composite. So it's valuable to examine this on a more power level kind of term or expression. So here I just found, first of all, the square root is 1/2 power. We could bring that whole base up to the numerator by negating the exponent, and now it's going to be a lot easier to differentiate. But first I will identify my inner function, x cubed minus 5. The outer function is x to the negative 1/2. And take the derivative of a composite by taking the derivative of the outer function depending on the inner function, multiply that by the derivative of the inner function, and we get all our points. We could use that to purchase the love of our parents. Now, we keep on going. Notice again, I can't stress this enough, set up your derivative first and then take the derivative. There's levels of complexity are only going to increase from here, and if you don't learn the discipline to write down your thoughts succinctly, then as the work becomes more complicated, you're going to have a harder and harder time keeping it straight, and your achievement will suffer as a result. Anyway, 3 times negative 1/2 is negative 3/2. Negative 1 minus 1/2 is negative 3/2. The derivative of x cubed minus 5 is 3x squared, and everything that happens afterwards is strictly cosmetic in nature. Obviously, this is one that definitely will require a technology check because there's a lot of things that could have gone wrong with my understanding, and fractions and negative exponent fractions, and on and on and on it goes. So, I hope this is helpful. I do intend to perhaps include a video that describes why the chain rule works a little bit better, but I'll have to wait into the future for that to happen. But anyway, thanks for watching. Have a good day.